Hello everybody, thank you for joining. Let's continue our discussion about Geomipmapping, which is an algorithm that enables you to add continuous level of detail to your terrain mesh. This basically means that parts of the scene which are closer to the viewer are rendered in a higher resolution compared to what is in the background, which is rendered with less detail. And this can potentially reduce the amount of compute that the GPU needs to do, while increasing the overall quality of the scene or the frame. Now, in the previous video, we saw an overview of the algorithm and we talked about some changes that we need to make to the layout. What we will do today is to go deeper into the level of detail, or LOD. We will see how to manage different LODs, how to create them for the same patch, and also how to avoid cracks in the terrain if you're not careful. But we will be careful, so our terrain will be bulletproof. Alright, before we get started, I'd like to say a big thank you to Andrew Diggs, who recently joined the OpenGL Underground. If you too would like to support this channel, you can do that at patreon.com/OGLDEV or by joining the YouTube channel as a member. Now let's see how to create different LODs for our patches. So in the previous video, we've made changes to our triangle layout, and now we're using this triangle fan structure. And we've said that the 3x3 patch is the highest LOD that we can support. And in the case of a 3x3 patch, we only have a single LOD. We can't go lower than this. If we have a 5x5 patch, and remember that I'm counting vertices, okay, so 5 vertices and 4 segments. So this is how LOD0 looks like. Okay, so we have 4 triangle fans here. And in this case, we have an additional LOD, which actually looks like LOD0 with a 3x3 patch, right? So this is LOD1, 5x5 patch. So what we're doing here is that we are skipping those vertices right here in order to create the layout as a triangle fan. So this looks like a 3x3 patch, okay? So those vertices are still there. They're part of the vertex buffer. But our indices are going to be laid out in a way which will skip some of the vertices to create a single triangle fan for the 5x5. So let's see 9x9. Okay, so now we have 4x4, so 16 triangle fans in LOD0. And if we go to LOD1, this actually looks like LOD0 of a 5x5 patch, right? And if we go to LOD2 of the 9x9 patch, so now we're skipping 1, 2, 3, 4 vertices in order to create a single triangle. Another 1, 2, 3, 4, and we create a triangle. Okay, so for a 3x3 patch, we have a single LOD. For a 5x5 patch, we have 2 LODs. And for a 9x9 patch, we have 3 LODs. And again, we can't go any lower than this. So a larger patch with more LODs means that we have more flexibility in terms of levels of resolution that we can support, but it also means that we have more indices to maintain, which can also translate to GPU resources. So this is something that you will need to tune for your game and depending on the platform. And we can also see a 17x17 patch. And here we have 8 triangle fans over 8, so 64 triangle fans. And I only got a single LOD here because I'm too lazy to create the other ones. But you can imagine that LOD1 would look like this, and LOD2 would look like this, and LOD3 would look like that. Okay, so if we need to formalize the procedure of creating the LOD, we can see that on LOD0, and this regardless the size of the patch, we need to skip 2 vertices along the x-axis and the z-axis, and then create a triangle fan from what we've got. But if we are on LOD1, like that, then we need to skip 4 vertices, 1, 2, 3, 4, and get to this point, and then create a triangle fan while skipping a single vertex for each triangle segment. So this means that we need to raise 2 to the power of the LOD plus 1. Okay, so for LOD0, that's 2 to the power of 1, so that's 2 vertices like that. And in the case of LOD1, that's 2 to the power of 1 plus 1, so 2 to the power of 2, it's 4, and we get to this point. And in the case of LOD2, that's already 2 to the power of 3 and 1, 2, 3, 4, 5, 6, 7, 8 vertices, and then create a triangle fan. So to summarize the LOD creation rules, the triangle fan is constructed from a subgrid of 2 to the power of LOD plus 1 vertices. Okay, so if we are on LOD0, this means that we need to skip 2 vertices and create a triangle fan from a subgrid of a 3 by 3. Okay, so we saw that in this case, for example. So every 3 by 3 vertices create a triangle fan. If we are on LOD1, we skip 4 vertices and create a triangle fan from a subgrid of a 5 by 5. So this is an example on LOD1. We have a 5 by 5 vertices and we have a single triangle fan inside. And in the case of LOD2, we skip 8 vertices and create a triangle fan from a subgrid of a 9 by 9. And this is the example. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices over 9 vertices and a single triangle fan. And once we've done that, we need to continue based on the size of the patch and tessellate the entire patch with triangle fans. Okay, so depending on the size of the patch and the current LOD, we will need to traverse the entire patch and create those triangle fans. Alright, so let's talk about crack management. And here we can see an example of cracks in the terrain. And the reason that we are getting those cracks is that we will obviously have 2 patches of different LODs side by side. Okay, so if we have a 5 by 5 patch, as in this example, we have LOD0 on the left-hand side and LOD1 on the right-hand side. We can see that we have 2 triangles in this patch versus 1 triangle in this patch. And what this does, if we look at it from kind of like the side, we can see that here we have a single edge. So the height is interpolated across the edge, but on this side, on the higher LOD side, we have another vertex here, which creates 2 edges. So this is the true height. And then the height is interpolated along this segment and along this segment. And those are obviously different. And then you can see the crack as in this case. Okay, so this is the top-down view. And this is basically the same thing. You can see the 2 triangles here and 1 triangle there. So the solution to this problem is to simply drop the vertices on the shared edge on the higher LOD side. So in this case, we drop this vertex right here, and then we get a single triangle on each side with a shared edge. And then the problem is gone because the height is interpolated exactly the same on both sides of the shared edge. Okay, so let's try to formalize the solution to this problem. And here we can see a 17 by 17 patch. We have LOD0 next to LOD1, next to LOD2, and we expect the problem to be along the shared edges right here because we have an extra vertex here that we said that we're going to drop. And also on this side, there is always 1 vertex, extra vertex that we need to drop on the higher LOD side. And what we can see is that we can kind of divide the patch into 2 parts. So we have a ring here, and the rest is called the core of the patch. The same goes here. There's a ring of triangles all around, and then the core, and the same is here. So let's see the problem in a different way. This is an actual screenshot of the implementation. And if we focus on this part right here in red, we can see that the problem is limited to the ring, right? Because we have the problem right here with those vertices, which are now gone because this is the actual implementation which solves this problem. But we can see that this part of the ring is different from this one, right? Here we can see those extra vertices because on this side we have no problem. So we have the full triangle fan on both sides. But in this case, this is kind of a degenerated triangle in a way. We lost those vertices, and now we have a single triangle which matches the triangle fan on the other side. And here we can see another example. Going further into the terrain, we can see the problem on this side of the ring. So this belongs to the bottom patch, which is a high resolution. And in this case, this ring, this part of the ring, is already part of this patch, a different patch. So this is a higher LOD compared to this one, and we need to drop those vertices right here. And here we can see the entire terrain. The patches at the bottom closest to the viewer need to match themselves to this area right here along their ring. And then these patches needs to match themselves to these ones. And then again right here. Okay, so let's try to formalize this. Okay, so the patch is composed of a core and a ring. The ring has 4 sides, and the patch LOD may be different from its neighbors on all 4 sides, but the delta can't be more than 1. Theoretically, you can support a case where, for example, LOD 4 is next to LOD 0, but this means that the number of indices will grow exponentially, and I'm trying to keep this a bit under control, so I've decided to have the delta no more than 1. Okay, so LOD 0 can be next to LOD 1, but not LOD 2, 3, etc. LOD 1 can be next to LOD 2. And the handling is always on the higher LOD. Okay, so if I'm on LOD 1, I need to make sure that I can adapt myself to LOD 2, but not to LOD 0, because LOD 0 will need to adapt itself to me. So the bottom line is that we will maintain a separate LOD for the core and for each of the 4 sides of the ring. And since the camera is dynamic, we have to support every possible combination of a patch and a neighbor. Okay, so for example, if we are on LOD 0, if our core is on LOD 0, so the first combination is where the core and the entire ring is on LOD 0, and this means that the patch is surrounded by LOD 0. Another case is the core is LOD 0, but the left-hand side is 1 and the rest are 0. Okay, so you can imagine that we have a patch of LOD 1 on the left side, and on the top, right, and bottom edges or sides we have LOD 0. And then theoretically there can be a combination where 2 sides are on LOD 1 while the rest are 0. Okay, and 3, and eventually where the core is LOD 0 and all the rest are LOD 1. Okay, so the total number of permutations is 2 to the power of 4, which is 16. Okay, so in practice, how exactly are we going to manage all those indices and switch between them? The idea is that we have a single index buffer, large index buffer, and we have a vector of something which is called LOD info. And the number of elements in this vector depends on the number of LODs. Okay, so in this example, we have 1, 2, 3, and maybe more. And for each LOD, we will have a corresponding element in this vector. And the LOD info itself is actually a 4-dimensional array of single LOD info structure, which we will see in a second. And we have 4 dimensions here for the left, right, top, and bottom. Okay, so the core LOD is determined on this top level vector. And once you find your LOD, you go inside to find a single LOD info structure. And then depending on whether you are on the same LOD as the core, you will access element 0 in each dimension according to the location of the camera. We will talk about this later. And if you need to go 1 LOD lower, then you will access the second element in each dimension. Okay, so we have a total of 16 single LOD info structures, and each single LOD info has a start and a count, which are integers. Okay, so the start tells us where to begin inside the index buffer, and count tells us how many indices we need in order to render the patch in this combination. Okay, so if you need to render LOD 2, you need to go to this guy, and then you go here, and then you need to find, for example, 0, 1, 1, 1. So you will go to the first element here, second element here, second element, find the corresponding single LOD info, go to the location where the start points to, and then the number of indices that you need to render is in the count element. Okay, and so the index buffer is prepared for any possible combination of LODs in the core and in the ring around it. Okay, so let's see the changes that we need to make to our Geomip grid class. This class represents the entire grid of triangles on the terrain. We have the patch size here in vertices, and we also have a maximum LOD. The maximum LOD is, of course, based on the patch size, and this will be calculated by the LOD manager, which will be covered in the next video. Here's the vector of LOD info, exactly as we saw. Here's the LOD info structure, and left, right, top, bottom are defined to be 2 for convenience. Single LOD info is here, and this is our start and count. Okay, so when we create the Geomip grid in this function, we need to initialize the LOD manager. We need to provide it with the patch size, the number of patches on the X and Z axis, as well as the world scale. Let me remind you that the world scale is a value which you provide when you initialize the terrain, and it is multiplied right here by the X and Z coordinates of the position vector. Okay, so this allows you to create kind of a low poly terrain. If you have a large world scale, it means that your triangles are larger and it seems like a low polygon mesh. Okay, so the LOD manager returns the max LOD, and we will see how it calculates it in the next video. Now we take the max LOD and we use it to resize the LOD info vector. Okay, so we need to add 1 to max LOD, because if the maximum LOD is 0, we need to resize it to fit one element, and this is what we do here. If max LOD is 3, we need to resize it for 4 elements, okay, and etc. Okay, so in the function populate buffers, we initialize the indices inside this vector. We have a vector of unsigned int for the indices, and we need to resize it according to the number of indices for this patch, which is now a bit complex. We will see that in a second. Now this vector is initialized on the stack, and then it is loaded into the element array buffer in this call to GL data. So previously, calculating the number of indices was very simple, but now we have several levels of LOD that we need to support for the ring. So we have this function to do that. We start at LOD 0, and in LOD 0, the total number of quads that we have is patch size -1 times patch size -1, because that's the number of segments. So you raise it to the power of 2, and this gives you the total number of quads in the patch. We initialize the total number of indices to be 0, and the maximum permutations per level is, of course, 16. And for each quad, of course, we have 6 indices. So what we do here is that we traverse all the LODs, and notice that we have smaller than or equal to the maximum LOD, because this value needs to be inside the loop. Okay, so we have this guy, and then we accumulate the number of indices into the total sum. And what is the number of indices in this level? This is the current number of quads, which is at the beginning, or on LOD 0, this is the maximum, times 6 indices per quad, times the number of permutations. And now we need to go to the next LOD. So we need to divide the number of quads by 4. Okay, let's see an example with a 5x5 patch. At LOD 0, we have 4x4, 16 quads, but in the next LOD we have 4 quads. Okay, so to go from this to this, we need to divide the total number of quads by 4. Now you may argue that the number of indices is different for each permutation, but this is not expressed in this formula right here, and this is correct, of course, but notice that the number of indices is returned from calc_num indices, and then we use it to resize the indices vector, but the function that actually initializes the index vector returns the true number of indices, which will be calculated dynamically during this operation. And then we use this value of num indices here when we call GL buffer data rather than this guy right here. And we can see an example here with a patch of 65 by 65 vertices. So we have 6 levels of detail, and we can see the total number of indices per LOD. And then the final number of indices is 518 something thousand indices. And the initial number of indices was 524,000 indices. Okay, so this difference comes from the different permutations. And then this number is used to initialize the actual index buffer on the GPU rather than this one, which is only used for the vector. Okay, so now that we have enough space in our indices vector, we need to actually initialize the indices for each LOD. This is done in the function init_indices right here. This function receives the indices vector as a reference. So what we do here is that we traverse all the LODs. Again, be careful not to miss the last one. And then we call a function called init_indices_LOD to initialize a single LOD. And the way this works is that we start at index 0. Okay, we start at the beginning of the buffer and we provide the index to this function as well as the vector and the LOD. And this function returns us the index for the next LOD. So each time we call init_indices_LOD, we pass in the index where this function should start writing, and then it gives us back the location where the next iteration should begin. Okay, so eventually when this function returns, we get the total number of indices that have actually been written into the buffer, and this goes back here, which is used to initialize the index buffer on the GPU. So now let's go to the level of a single LOD. Again, we get the index, the vector, and the current LOD. Okay, so we need to traverse all the permutations, all the 16 permutations of left, right, top, and bottom. And we access the LOD info vector. This LOD is for the core, and these guys are for the sides. The start is, of course, the index which was provided here. Next, we call init_indices_LOD single for this specific combination of core and sides. And again, this will return us the index. So the number of indices for this iteration is the new value of index minus the start of this iteration, right? And we also accumulate this number of indices into the total indices for LOD, but this is only for printing, so it's not actually required. Now for the call to init_indices_LOD single, we provide the starting index, the vector, the LOD of the core, and then for each side, it depends on the value inside the corresponding for loop. Okay, so this is either exactly like the LOD if we are on 0, or this is LOD plus 1 if we are on the second element and we have the specific value for each side. Oh, look at that. It's nighttime already. I guess time really flies when you're having fun. So, where were we? Yeah, so create triangle fan also returns the index, which is the next location to be written into the index buffer. Again, this is the same way that all these functions in this call stack work, right? So we start at init_indices, which traverses all the LODs, and then init_indices_LOD traverses all the permutations of a single LOD, and then init_indices_LOD single traverses the patch at this combination of LOD for the core and the 4 sides, right? So what we need to do is to go over the entire patch and create as many triangle fans that fit into the patch. Now, we need to stop before the end of the patch. So we calculate something which is called fan step, which basically tells us how many vertices we need to step in order to get to the next patch. All right. So for example, if we are on LOD 0, we need to step exactly 2 vertices. Let's see that. On LOD 0, we need to step 2 vertices to get us to the next triangle fan. right, on both axes. And in the case of LOD1, we need to step 1, 2, 3, 4 vertices in order to get us to the next triangle fan if there was one right here or over there. So the formula is 2 to the power of LOD core plus 1. And now we can calculate the ending position, which is where we need to stop inside the patch. Okay, so we take the patch size, subtract 1, as well as the fan step that we just talked about. Let's see an example. Let's say that we are here, okay? In this case, the fan step is 2, as we've seen. So this is the patch size, the number of vertices here. And then we subtract 1, so this gets us to the location of the last vertex. So subtract 2, and this takes us to the location where the last triangle fan begins, right here. So we traverse the patch, and this is where it gets a bit more complex, because we have triangle fans here inside the core, where there will never be a problem, because this triangle fan will always be complete, right? We never need to skip any vertices. But in this case, this one, it all depends on what is the LOD of the ring, of the left-hand side of the ring. If, for example, the LOD here is 1, it means that we need to skip one vertex here, so we need to step 2 vertices in order to create a single triangle. But in the case of the top, where there isn't a problem, we need to step 1 vertex and then another, and not 2 as in this case. Okay, so we need to check whether the triangle fan is located on the first column, or the last column, or the first row, or the last row. And this will tell us whether we need to do something special about the edges of the patch. And we have this check right here. Okay, so if x is 0, then the LOD for the left-hand side will be LOD left, which was provided as a parameter, because remember, this is a specific permutation. But if it's not 0, then the LOD of the left will be the LOD of the core. And then, if it is, then we have the LOD of the right, again provided here. If not, LOD of the core, and same for the bottom. Check if Z is 0, and for the top, whether Z is the ending position. So now that we know the specific parameters for this triangle fan, we call create triangle fan with the parameters, and this takes us to the next function. So now we need to do the same thing, raise 2 to the power of the specific LOD, and this tells us how many vertices we need to step along the left, right, top, bottom, and also how many vertices we need to step in order to get to the center of the triangle fan. And this is the first index that we calculate. We add the step center to the Z, we multiply that by the width of the patch, add X, and again, step center. So in this case, for example, if step center is 1, and we are here, this is X over Z, then we add 1 to X, this gets us here, add 1 to Z, and this gets us here. But in order to calculate it as a one-dimensional array, we need to multiply the Z by the width of the patch, and then add the X plus the step center, and this will take us to the correct location of the center. So now, following the same logic, we calculate 2 indices. We call them index temp 1 and index temp 2. We saw that in the previous video, so you should definitely watch that. And these guys designate those 2 vertices here. Okay, so this is index temp 1 and this is index temp 2. And now we can create a triangle from the 3 vertices, those 2 plus the center. And this is what happens here. Again, we get the index where we need to continue. And now we need to do another test. Okay, we need to check whether the LOD of the left equals to the LOD of the core. If this is the case, then we need to do another step on the left and create another triangle. This is what we're doing here. Index temp 2 is copied to index temp 1 and index temp 2 moves forward. Okay, so index temp 1 becomes this guy and index temp 2 becomes this guy, and this allows us to create another triangle. And now we start going to the right, and this is basically the same thing. You can see copy index temp 2 to temp 1, and index temp 2 moves forward, based on the current location inside the triangle fan. Okay, so top, right, and bottom. And on each side, we need to do a check. And if the LOD on this side equals to the core, we create another triangle. Otherwise, we will skip it, and then we will get this triangle here, if this is the top, or this triangle on the right, or this triangle on the bottom. And now that all the indices have been hopefully created successfully, we can continue to the render function. So as I've said, we're going to cover the LOD manager in the next video, but what it needs to know is the camera position. So we provided to it on the update function. And now the LOD manager knows which LODs we need to use for each patch, depending on the location inside the grid. Okay, so we traverse the grid over the number of patches on the Z and the number of patches on the X. So we ask the LOD manager which LODs we need to use for this specific patch, and we get those LODs here. Next, we need to calculate the location in the index buffer for this specific permutation, but this is very easy because we have all the LODs here. So all we need to do is to use the LOD of the core to access the LOD info vector, and then the other 4 LODs for the left, right, top, bottom, they are used to access this guy right here. And now we know the start and the number of indices that we need to render for this specific patch. Now for the call to GLDrawElements base vertex, we need to provide the offset in bytes inside the index buffer. So what we need to do is to multiply the starting index by the size of unsigned int, because each index is an integer, and this is now an offset in bytes, which is cast to void pointer. This is how this function works. And of course, the number of indices is provided in the count element of this structure. Yes, we have the start and the count. And the last thing that we need is to add a base vertex, because we are reusing the same set of indices for each patch, but each patch corresponds to a different location inside the grid. So we need to provide a base vertex, which will be added to each index. And this is calculated here. This is the coordinate of the bottom left corner of the patch. And we provided as the last parameter to GLDrawElements base vertex. So let's run this. Click on W to switch to wireframe. And now we can move backwards. And we can see the change in the LOD at some point, and this is the lowest LOD that we can get to. If we move forward, we are adding detail, going to a higher LOD, and I think this is the last one. Oh, this is the last one. Okay, this is a big patch, lots of LODs here. Okay, so I hope you enjoyed this video. If you did, please hit the like button and subscribe. Thank you for watching, and I hope to see you in the next episode of Terrain Rendering.